Have you ever wondered what happens if you fall into a black hole? Where do you go? Does everything just disappear? It's one of the biggest mysteries in the universe. And today, we're diving deep into this cosmic rabbit hole. So, let's set the scene. Imagine you're an astronaut, floating peacefully in space, and you get a little too close to a black hole. As you approach the event horizon, the point of no return, something bizarre starts to happen. From your friend's perspective, watching safely from a distance, you would appear to slow down, stretch out, and eventually freeze in time, slowly fading away. This is because the black hole's immense gravity warps time itself. For your friend, you never actually cross the event horizon. But for you, the journey is just beginning. Once you cross that invisible boundary, there's no turning back. The gravitational pull is so strong that not even light can escape. You're now inside the black hole. What happens next depends on the type of black hole. If it's a relatively small, stellar mass black hole, the tidal forces would be extreme. The gravity at your feet would be so much stronger than the gravity at your head that you'd be stretched into a long, thin strand of atoms, a process scientists colorfully call spaghettification. Not exactly a pleasant experience. But what if it's a supermassive black hole like the one at the center of our galaxy? These cosmic giants are so huge that the tidal forces at the event horizon are much gentler. You could actually cross the event horizon without being immediately torn apart. You'd be falling and falling in complete darkness as all light is being pulled inward with you. According to Einstein's theory of general relativity, everything that falls into a black hole is destined for a single point at the center, the singularity. This is a point of infinite density and zero volume, where our current laws of physics completely break down. At the singularity, space and time as we know them cease to exist. All the matter and information that made you you would be crushed into this infinitesimal point, effectively erased from the universe. That's the classical picture, at least. It's a one-way trip to oblivion. But this idea creates a huge problem for physics, known as the information paradox. One of the fundamental rules of quantum mechanics is that information can never be destroyed. Information, in this sense, is the unique arrangement of all the particles that make up an object. If a book falls into a black hole, the information contained in its pages, the specific sequence of atoms and molecules should, in theory, still exist somewhere. If the singularity just destroys it, then one of our most basic physical laws is wrong. This has kept physicists up at night for decades. So, what's the solution? This is where things get really weird and wonderful. The late, great Stephen Hawking came up with a groundbreaking idea. He proposed that black holes aren't entirely black. Due to quantum effects near the event horizon, black holes slowly emit a faint glow of particles, now known as Hawking radiation. This radiation causes the black hole to lose mass over an incredibly long time, and eventually, to evaporate completely. This raises a new question. What happens to the information that fell in? Does it escape with the Hawking radiation? For a long time, Hawking thought the information was truly lost forever. But this contradicted quantum mechanics. He later changed his mind, admitting it was his biggest blunder. He and other physicists started to believe that the information must somehow be preserved. So, how does it get out? There are a few competing theories, and none of them are proven yet. One popular idea is the holographic principle. This suggests that all the information about the three-dimensional stuff that falls into a black hole isn't actually inside it. Instead, it gets encoded on the two-dimensional surface of the event horizon, like a cosmic hologram, as the black hole evaporates via Hawking radiation. This information is slowly released back into the universe. It would be scrambled and almost impossible to decode, but technically, it wouldn't be lost. So, The information that made you would be imprinted on the boundary of the black hole and then slowly radiated back out into space over trillions and trillions of years. Another, even more mind-bending idea is that a black hole could be a gateway to another universe. Some theories suggest that the singularity at the center might not be a point of infinite density after all. Instead, it could be a wormhole or an Einstein-Rosen bridge, a tunnel through space-time that connects to a different point in our universe, or perhaps a completely separate universe. In this scenario, anything that falls into a black hole is shot out the other side through what's called a white hole. A white hole is the theoretical opposite of a black hole, a region of space-time that nothing can enter from the outside, and from which matter and light are constantly spewing out. If this is true, then falling into a black hole wouldn't be the end, but the beginning of a journey to somewhere else entirely. However, we have no evidence that white holes or stable wormholes actually exist. They are purely mathematical possibilities for now. There's also the firewall hypothesis. This idea tries to solve some of the paradoxes created by Hawking radiation. It suggests that right at the event horizon, there's a wall of high-energy particles, a literal wall of fire. Any object attempting to cross the event horizon would be instantly incinerated by this firewall. This would preserve the laws of quantum mechanics because the information about the object wouldn't be duplicated both inside and outside the black hole. But it creates a new problem. It violates Einstein's theory of general relativity, which says that an astronaut falling into a large black hole shouldn't notice anything unusual. As they cross the event horizon, it's a classic physics showdown. Einstein versus quantum mechanics. So, where does that leave us? Did the stuff that fell and get crushed at the singularity encoded on the event horizon or shot out into another universe? The honest answer is we don't know for sure. Finding the answer is one of the biggest goals of modern physics because it would require a unified theory of everything, a theory that successfully combines general relativity, our theory of gravity, and the large-scale universe with quantum mechanics, our theory of the very small. Scientists are working on this. We're observing black holes with powerful telescopes like the Event Horizon Telescope, which gave us that first incredible image of a black hole's shadow. We're also studying gravitational waves ripples in space-time created when black holes collide. These observations are giving us unprecedented data that can test our theories about gravity in its most extreme form. Every new piece of data helps us chip away at this cosmic enigma. So, while we can't send a probe into a black hole to see what inside it would never be able to send information back, we can study them from the outside. The quest to understand what happens inside a black hole is really a quest to understand the fundamental laws of our reality. It pushes the boundaries of our knowledge and imagination. So, can we ever find the things that fell into a black hole again? If the holographic principle is correct, then yes, in a way. The information that made up those things would be scrambled and radiated back out into the cosmos over an unimaginably long time, but reassembling it would be practically impossible. If the wormhole theory is right, those things might exist somewhere else entirely, forever beyond our reach. And if the classical view is correct, they are simply gone, crushed out of existence. It's a mystery that touches on the very nature of space, time, and information. What do you think happens? Does the information escape? Or is it lost forever? Let me know your theories down in the comments. If you enjoyed this deep dive, don't forget to like, subscribe, and hit that notification bell for more explorations into the biggest questions of the cosmos. See you next time!